Hello and welcome to today's video. In this video, we're going to talk about something that you've all been longing for since we introduced function limits, and that is going to be L'Hopital's rule. So, topic of this section is L'Hopital's rule. And for those of you who have never heard of L'Hopital's rule, let me give you a quick introduction and motivation. The idea is to simplify and ultimately determine limits of a certain kind, and that is fractions that look like this. So we have a function f, we have a function g. We want to determine the limit of f divided by g for x tending to some value x star in a situation where both f of x star and g of x star are 0. Now you might know there's also a variation of L'Hopital's rule that allows for both values to be infinity or minus infinity. In the motivation, we're going to focus on that one case where both are 0. In the theorem that we're going to formulate right afterwards, of course, we'll include all possible cases here. The main idea that L'Hopital's rule is based on is approximation. You remember that we introduced the derivative of a function through the approximation at a given point through a affine linear function. And we can now use this idea to simplify limits of that kind here. So the basic idea is to use approximation. More specifically, let's say f and g are differentiable, not just at x star, but in some interval around x star. So that can reasonably approximate those functions around the point in question, which is x star. So f and g are differentiable let's say in some interval around x star. Then we can approximate the functions f and g in some vicinity of that point x star. So as long as we're close to x star, we can obtain a good approximation through the derivative. So what we obtain there is, for x close to x star, we have the following. We have that f prime at x star. You know that by definition, f prime at x star is the limit of the following expression here, f of x minus f of x star divided by x minus x star. And we take the limit. Now, instead of taking the limit here, we can also say, as long as we're close enough to x star, this derivative is approximately equal to this expression for all x that are close enough to x star. And what that means is that we can approximate the function f by simply solving this for f of x. So f of x is approximately f of x star plus f prime of x star times x minus x star. So this is the basic idea of approximation of the function f through an affine linear function. And basically that function is determined mainly by the derivative at the point x star. Of course, you can also see that at the point x star, this here becomes 0. So we exactly get f of x star. So the approximation is precise at x star. And as we move away from x star, it of course will get worse, unless we start with an affine linear function in the first place. But usually this approximation, this here, will be different than the function f itself. But if we close enough to x star, it will still be a nice, good approximation. And of course, we can do the same thing for g. So g prime of x star is approximately equal to g of x minus g of x star divided by x minus x star. And that means g of x is approximately equal to g of x star plus g prime of x star times x minus x star. And now let's say g prime of x is not 0, then we can of course have a look at the ratio of f to x to g of x. So if g of x is not 0, then we may expect the following. We may have a look at f of x over g of x. And that is approximately equal to, let's take these approximations here. F of x is approximately equal to this. G of x is approximately equal to that. And remember, we know that f of x star and g of x star are both 0. So we only have these terms here left. And that means what we get here is approximately f prime of x star times x minus x star over g prime of x star times x minus x star, which of course is the same as f prime at x star over g prime at x star. And thus, of course, if we take the limit of that expression, f of x over g of x as x tends to x star, then we'd expect that to be approximately the same as the limit of x to x star over f prime of x, g prime of x, which is in the limit this expression here. Of course, this is not a rigorous proof of L'Hopital's rule. We have to put in some more work to obtain that rigorous proof, but it does capture the essential ideas of that proof. So again, not a rigorous proof, but it does capture the main idea. And now let's actually formulate L'Hopital's rule. So that is going to be the central theorem of that video. Theorem that's known as L'Hopital's rule. And as I said, that theorem is a little more general than what we discussed right above. So as usual, we talk about functions defined on an open interval. So let I subset of R be an open interval. And let f and g be functions defined on that open interval with values in R that are differentiable on I. Also, we want g prime of x to not be 0 for all x in I. Then, if for a certain point x star in I, we have that the limit of both f and g for x tending to x star is either 0 or infinity or minus infinity, but both equal. That's important. So it's either 0, 0 or infinity, infinity. Then we can apply this L'Hopital's rule. So if for a point x star in I, we have that the limit of f of x as x tends to x star is equal to the limit of g of x as x tends to x star. And both limits are either 0 or minus infinity or plus infinity. Then we can apply L'Hopital's rule, and that says the limit of f of x over g of x for x tending to x star is equal to the limit of f prime of x over g prime of x, again, for x tending to x star, if, and that's an important point, if that latter limit actually exists. So if this limit here does not exist, for example, if it's infinity, that means the limit doesn't exist, then this limit here need not necessarily be infinity, or it could still exist, even if that does not. But in case this limit does exist, we can apply that rule. Okay, so you can derive a limit that way if it exists. You cannot state that a limit does not exist because of that rule. And one more remark here, the statement also holds for one-sided limits, of course. Now, let's just see two quick examples about easy applications of L'Hopital's rule. We'll see some more examples on variations of that technique in a later video. So the first example we're going to look at is the limit as x tends to 0 of the following expression: x times 1 plus x to the power of n divided by 1 plus x to the power of n minus 1. And as you can see, x of course tends to 0. 1 plus x tends to 1, so this expression tends to 1 to the power of n, and that means the numerator itself tends to 0 times 1, so to 0. The denominator, this here tends to 1 to the power of n, and of course this here is equal to 1, so the whole denominator also tends to 0. And that means we are in a 0 divided by 0 situation here, so we can try to apply L'Hopital's rule. Both functions are obviously differentiable over R, so there's no problem with differentiability. So we'll apply L'Hopital's rule, and I'll indicate that by writing an LH over the equality sign here. And of course, I advise you do the same so that the correctors in the exam know what you're trying to do there. Just in case you make a mistake there, at least your intention is known. So let's compute the derivatives. To compute the derivative of this expression here, we need product rule. We start by differentiating x. So the derivative of x is 1. And we just copy the 1 plus x to the power of n expression. And then we add x times the derivative of this expression here. And that is n times 1 plus x to the power of n minus 1. And then if we apply chain rule and differentiate that inner expression here, the derivative is 1. So that doesn't add anything new. For the denominator, we again have this expression here to differentiate. The derivative is n times 1 plus x to the power of n minus 1. And minus 1 differentiated is just 0, so that vanishes. So as you can see, that simplifies the expression quite a bit. So that leaves us with x tends to 0. And you can see that this expression here, 1 plus x to the power of n minus 1, that appears here and also here implicitly. So we can cancel that out. And what remains is 1 plus x. So this is this here divided by that expression, plus x times n. And in the denominator, n. And so if we now take the limit here, the denominator doesn't contain x anymore. So this expression tends to 0, this tends to 1. So the numerator tends to 1. The denominator is constant anyway. So what you get is 1 over n. And that is the limit of that function for arbitrary n. Now, let's see one other example. I said that this rule can also be applied for fractions of the type infinity divided by infinity. So we'll see one example for that. Let's say we have some epsilon that is positive, and again some arbitrary n. And we'd like to compute the limit of the following expression: x to the power of n divided by 1 plus epsilon to the power of x, as x tends to infinity. So here we have x and then to a constant power, and here we have an expression that is almost 1, very close to 1, to the power of x. Basically the question is, which of these wins? As you can see, both numerator and denominator, of course, tend to infinity for x to infinity. And both are differentiable functions, so we are again in a situation where we can apply L'Hopital's rule. And if we do that, we get the following limit. So in the numerator, we just obtain n times x to the power of n minus 1. For the denominator, remember the rule for differentiating functions of that kind, something to the power of x. The derivative of that is always ln of the base, which is 1 plus epsilon here, times that expression as it was, so 1 plus epsilon to the power of x. So you can see that again, we have infinity over infinity here. And again, we have differentiable functions. So if that is the case, let's try to apply L'Hopital's rule once more. And if you do that, what we get is following. So in the numerator, we obtain n times n minus 1 times x to the power of n minus 2. In the denominator, this is constant as far as x is concerned, so we only have to differentiate that. And we know how to do that. That produces another ln 1 plus epsilon factor here. So we get that factor 2 times squared times 1 plus epsilon to the power of x. And again, we're in the same situation. We have differentiable functions in numerator and denominator, and both tend to infinity. And we can, of course, just repeat that process almost indefinitely until we have used up all the n's up here. So when this here becomes a constant, of course, that process stops because the derivative of a constant would then be 0. Plus, if we have a constant here, it's not going to tend to infinity anymore. And when does it stop? Well, it stops once we have taken the nth derivative of that whole expression. So that stops after taking n steps. And what we get is in the numerator, n times n minus 1 times n minus 2 times n minus 3 and so on up to times 2 times 1. So that is n factorial. And in the denominator, we'll have ln 1 plus epsilon to the power of n and still 1 plus epsilon to the power of x. that factor always reproduces, so that will not vanish no matter how often we differentiate. And now we're in a situation where the numerator is a constant, so that of course tends to that precise constant. That doesn't depend on x anymore. And the denominator still goes to infinity. So that means we can make this expression arbitrarily small by just choosing x large enough, and that means the limit here is going to be 0. So what we learn from this basically is that an exponential function, even with a very small base, always grows faster in the long run as any power of x. And that concludes this video. As I said, we have more examples in the following videos, and as usual, I hope I'll see you then.